change in theta is what happened. That's what I was wondering.
Okay.
So it's a gymnast, and she's doing some sort of like roll, some kind of flip or something. And basically, at the beginning, her speed of rotation, her angular velocity is 3 revolutions per second. So in other words, if she kept on rotating or spinning at that rate, she would do 3 complete revolutions in 1 second. But she's not doing that for a whole second. She's only doing that at that 1 instant of time. You know, it's an instantaneous angular velocity. Just like if somebody's going 55 miles per hour, that doesn't mean they're going to go 55 miles. That just means if they kept going that speed for an hour, they would go 55 miles. Yes? No?
Yes.
Okay. So this is how fast she's rotating initially, but during the roll, during the tumble, she actually tucks in and she rotates faster. So by the end, she's rotating with this angular velocity.
So all you have to do is find the average omega and then find the time.
Right.
Oh.
Right. So then we know that the average angular velocity is going to equal the initial plus the final divided by 2. So in this case, the average would equal 3 revolutions per second plus 5 revolutions per second all over 2. So on average, how fast is she rotating? 4 revolutions per second.
So then it's.
So that's one formula, one problem. And then the other relationship is average angular velocity is equal to the change in the angle divided by the time. And in this case, we know the average angular velocity is 4 revolutions per second. And her change in angle here is a half a revolution.
Does it give you that?
Yeah.
Well, what they say is a half revolution. They didn't say that. It was changing the theta by 1.
And then you have to figure out the time. And if you solve this for time, what does the time end up equaling? 1/2 divided by 4.
So 1/8.
0.125 seconds.
0.125?
Yeah.
Now, the thing that makes this a little bit trickier is normally we're not doing our angular velocity in revolutions per second. And normally we're not doing our change in angle in revolutions. Normally it's in radians. Yes. So if you wanted to, you could be like stricter with your units. You don't have to because everything jives if you just leave it in revolutions. But if you wanted to, you could go back to the original problem and say, hey, initially, what was her angular? 3? So you could say her initial angular was 3 revolutions per second. And you could convert it into radians per second. So basically, 1 revolution is how many radians? 2 pi radians. And since these two are equal, it's like multiplying something by 1 and like factor labeling. So then the revolutions would cancel out and you'd be with 6 pi, which is what, like 6.28 radians.
No, 6 pi would be bigger.
6 pi would be.
Oh, sorry. Whoopsie. What's 6 pi gonna be?
18.849.
Thank you. And then you could do the same thing for the final angular velocity. And then if you want, then what about your change in theta? Well, they said it was a half a revolution. labeling on that, and we know that 1 revolution is 2 pi radians, and that would come out to be what? 3.14 radians. So you can do the whole problem in radians and radians per second to get the time, and go back and use the same 2 formulas, but you didn't necessarily have to do that conversion. You could just leave everything in revolutions per second, because in the end, in this